Okay, good afternoon, or good evening, or good night, or good morning, whatever time zone you're in and watching this lecture. Just double checking on the sound. People can hear me?
Yes.
Yes.
Okay, super. Okay, I'm going to talk about two things today. I want to finish off our discussion of FaRM, and then I'll talk about Spark. And just to remind everybody else, or everybody where we were with FaRM, we're talked about executing a transaction without any failures. And we looked at one example of whether actually the transaction provided external consistency or strict serializability. And so I want to talk about one more example to talk about serializability, and then talk a little bit about fault tolerance. But before doing so, it's probably helpful to remind ourselves exactly how a transaction works if there are no failures. And so in FaRM, an application goes for two phases: the execution phase, where it fetches objects from different shards, and then the commit phase. And so if we look back at this picture here, in the execution phase, three objects are being read. One from each different shard. We have shard 1, shard 2, and shard 3, and every shard has one backup. So the system can tolerate one failure. So the objects are read. The two objects are being modified, as we see in a second. And then once the three objects are read and two are modified, the application might decide to commit, and then the whole commit phase goes into action. So this whole story from steps 1 through 5. In step 1, the transaction takes out locks on the objects that have been written. So we see here there have been two objects that have been written to by the transaction, and so we're propagating what's called lock records to every primary. So every primary is going to have a lock record for this transaction and for the objects involved in that transaction. And the lock record contains an object ID, which identifies the object uniquely, a version number. So at the time that the transaction reads an object, it gets back a version number. In fact, it gets back this 64-bit number, which in the top is a lock bit, and the rest is the version number. And then a new value. Primary 1 and primary 2 is going to have, primary 1 is going to have a lock record for object 1, primary 2 is going to have a lock object for object 2. Then there's a separate phase for the validation of the read-only operations, so operations or objects that are only be read but not modified. And as we can see in this validation step, the dotted lines represent one-sided RDMAs. And as we talked about on Tuesday, those basically involve no server involvement. The sender can just read an object out of the memory of the server without actually having to interrupt the computation that's actually running on the server. So they tend to be very fast, unlike these operations that we saw here, which are actually write RDMAs. They're cool too, in the sense that you get to write to the append to this log record without actually interrupting the server, but the server actually has to process these log records, and the server in this case, once it actually processes one of these log records, it tries to take out the lock. If it succeeds trying to take the lock, because for example the version number hasn't changed or the lock bit or no other transaction is taking the lock, then it will reply back using another one, a write RDMA, saying okay. And so we see that on the acquiring the lock requires action on the server, but the one-sided RDMAs for reads validation doesn't require any action on the server. Then there's if everything turns out to be okay, so the transaction is basically able to obtain all its write locks and validate the read operations, it actually makes a decision to commit. And to commit, it first communicates to every backup the object, the change. So it writes a commit backup record. And appends that to every to the backups of the objects that have been modified. And again, it's basically a copy of the BOC record. The OID goes in there, the version number goes in there, and the new value. Once all the backups have reported that they actually have a copy of the object. Now we're basically in pretty good shape, correct? Because the primary has a copy, the backup has a copy, except the primary doesn't really know if the transaction has been committed yet or not. And so a final step is that actually the coordinator or the transaction coordinator writes out a commit record, a commit primary record. Informing the primaries that actually the transaction actually has committed. And as soon as it gets an acknowledgement from one of the NICs, indicated by the dotted lines, it actually reports back to the application saying that the transaction committed. So what we want to do now is look at two cases. One, we wanted to talk a little bit more about the serializability, just to see if the concurrency control worked out, and then we want to talk a little bit about fault tolerance and see if the fault tolerance story works out. So let me first start with serializability. Or actually, maybe before doing that, let me just ask if there's any questions so far, and whether everybody sort of has successfully swapped FaRM back into your memories.
What does the rectangle mean in this picture?
Sorry?
So what's the rectangle? What does it signify along the
arrow? Oh, it's an object.
Oh, it's an object. Okay.
Okay.
Sounds good.
Okay. Any other questions? Okay, good. Let's so let's look at the correctness from the concurrency perspective. So the correctness is strict serializability. And on Tuesday, we looked at a transaction that didn't really involve a write validation because there was no object that was read but not written. And so I'm going to look at another transaction this time around where actually the validation phase plays a role. And so I'm going to look at two transactions. And this is this example is a classic example to test whether a protocol provides serializability or not. Of course, it's not going to be a proof, but it's one of these key examples that generally is very helpful to see, to understand how the protocol works. So the protocol, the transactions are if x is 0, then we're going to set y to 1. So if object x is 0, we'll set object y to 1. The transaction 2 is the opposite. It looks if y is 0, and if y is 0, we'll set x to 1. And the reason that these this is a good test for serializability is that either transaction 1 should go after T2, correct, or T2 should go after T1, and depending on which order you run, either y is 1 or x is 1, but you never should have the outcome that x is 1. Oops, that x is 1 and y is 1. And that should not be allowed, because that would definitely violate serializability. Does that make sense? Okay, so what we want to do is test whether FaRM actually is successful in, where we want to understand where FaRM actually indeed it is not possible that x is 1 and y is 1 get produced. So let's look at the timeline. Let's say here we have T1, here we have T2. Here's the timeline. So they both, in their the preparation or the execution phase, they both read these objects. So let's say they run truly concurrently. We do a read of x, get at version number 0. We do a read of y at version number 0. Same here. And of course, T1 will update Y, T2 will update X, and they basically at some point, both start sort of the commit phase. And so let's say the T1 start first, and basically it grabs the, it needs the lock on Y, since it's going to be writing Y. So let's say X successfully grabs the log on Y, and so that actually will set, the log bit, in the version number of the Y object. And then, let's say, it actually, since it's going to read, it has read X, but it's not, it has read X, but it is not modifying X, it's going to be validation of X. X was read at version number 0. At the validation phase, nothing actually has changed yet with X, so the version number is still 0 there. If we run executed in this order, and so things are sort of are fine, and at some point, this transaction might commit. So let's look at T2, and let's say T2 runs after the validation of X, so it grabs the log, and then has read Y, so it needs to do a validation of Y. And so it's going to do a validation of Y, and the question is that validation going to succeed or not?
No, because the other operation has a lock and modified the value, so it's not the same that was originally read.
Yeah, so the version numbers might be still the same, but the Y, T1 has set the lock bit, right, for the object of Y. And so at this point, this validation will fail because it's not the same, or the lock bit has been set. And so to T2 transaction, the T2 transaction will abort. Okay, does that make sense? So we see, at least in this particular example, that it is the case that T1 and T2 both don't commit, which would result in this incorrect outcome. Any questions about this?
I had a question.
Yeah.
Yeah. So like for the transactions, so these are like, these have to be like update transactions, like write. Correct? Like if it was read, it could do it.
Yeah, go ahead.
I was just wondering, like if they were like read operations, you could do that like lock free, right? And as long as the
so this is actually good. Let's go back to this picture here, correct? And let's look at let's say there were no writes involved in this transaction at all, right? Like, so for example, the two objects that are being read, correct, are stored at P1 and P2. So let's assume that these guys are actually not involved. So those objects were not written. So the only operation that's happening is a read of that object. And if you see and so the protocol is carefully designed so that if you only do reads, you only do one-sided RDMAs, correct? Here in the execution phase, and then one RDCA to do the validation. And no locks are taken out, no writes are being done, no records are being appended. That's the only thing that happens. And so this is one of the cool features about FaRM, is that these transactions that only do reads can be executed without with only one-sided RDMAs and with no writes to any logs or grabbing any logs. And so that's why one reason that they get extremely high performance. And this is also the reason why, for example, the lock phase, the lock step and the validation steps are two separate things, because for read-only transactions, there's no lock step. Okay.
Actually, a question on that. For read-only transactions, why do we need the why do we need the validation phase? Because aren't you like reading a value and then you're immediately validating right after it, like the version? It seems like
there could be another transaction that has modified the object yet. So if a transaction ran or started and committed before, a concurrent transaction that actually writes might modify the object. and that would be bad, right? So the transaction that writes, then the transaction that actually follows it, should see observe that last write.
But if they occur at the same time, then we can reorder them either way.
Yeah,
right?
if
So
they
we
occur
can-
exactly at the same time, we can reorder them. Yeah.
So it still seems to me like the second validation, because the first time you read it, the second time you just immediately ping and see if the version is the same. It still seems to me like the second validation is like almost unnecessary.
You might be right. I haven't thought very hard about this. That if there are transactions that are only read-only transactions, then this validation is undoubtedly not necessary. I haven't very carefully thought about like when there's a mix of transactions where there's a case where you need the validation.
Yeah, wouldn't that be the case where like you have like if you read a value, like you expect to read like two values atomically, you read a value, after you read a value, like some transaction modifies the other value.
Yeah, that'd be
But
one
no, but
possibility.
it doesn't. Yeah. Yeah, actually, I'm not quite sure actually in that case if that's a problem.
Like for example, in this case, this T1 and T2 case, it's really crucial that Y actually does the validation, correct? Even though actually that transaction, T1 only reads Y, correct? So,
What if transaction 2 was just x equals 1 instead of like without the if statement?
blind write?
Hmm?
If it's just a blind write.
Yeah, it's just x equals 1 and then it executes after the validation of T1.
Yeah, that's fine, correct?
But wouldn't in that
I'm not sure
case-
what the question is. Maybe
Oh,
that's-
so if T2 is just like right, like write x equals 1,
Yep.
wouldn't the validation step like after and it executes after the validation step of T1, wouldn't then T1 think that x equals 0, but then x becomes 1 before the commit?
Okay, so okay, maybe we can hold this up because I gotta redraw the whole picture and figure out exactly what the scenarios you're talking about. Okay, so maybe we can go back to this at the end.
Sorry, I had a question. What is the use case for read-only transaction?
If you think back at Spanner and this paper, like there's often the case in these workloads, the TPCC workload and the TATP workload, where there's a transaction that only does reads. For example, it computes the balances of a set of accounts. Nothing is being written, but a lot of accounts are being read.
Thank you.
Okay, so we see here that there's actually the validation phase is crucial, correct, for this T1 and 2TK transaction. And furthermore, that actually things not work out correctly. We get strict serializability. Of course, this is not a proof, but it gives you, this example that sort of tried to get at the tricky case. Actually, the FaRM seems to work out correctly. Okay, so that's on the concurrency control. Then the second part we want to talk a little bit about is fault tolerance. And just going to want to get I'm not going to go in great amount of depth here. Just want to talk about the key challenge and see and build some intuition why we might actually be hopeful that FaRM actually addresses that key challenge. And so the key challenge, so maybe I should have the key challenge is that the transaction order crashes after telling the application and then it has to be the case, right, that the transaction persists. Because we have informed the application that the transaction is committed, so we can't actually lose any writes that the transaction has done. And so we can look at this picture again and see if we're going to be hopeful that this is the case. So, there's a couple things to observe. After, the lock phase, it is the case that after the lock phase, it is the case that the two primaries, P1 and P2, have a lock record, which describes the update. We don't really know if the transaction, that record doesn't say whether the record actually, whether the transaction has committed, but we have information about the transaction. Then after this step, the commit backup step, we know that backup P1, B1 and B2 have the commit record. And then before the transaction, the transaction coordinator reports to the application that it has been successful, we know that one of the primaries, well, let's say P1, also has the commit record. So let's assume there's a crash, like right here. So at that particular, just after that commit point, and the system crashes. And what we want to convince ourselves of is that if there's one failure, so like for each chart, things actually work out correct. And so the worst case, basically, correct, is that B2 fails. So here, where is B2? Here's B2. B2 fails. And so we lose, that commit record that is actually there. The primary might actually have not a commit record yet, because it crashed after we received the acknowledgement of one primary. So let's say that P1 must actually have the commit record. So in this case, P1 will have the commit record. And and of course, the backup has a commit record for B1. And so this is enough information, correct, to convince the during recovery that actually the transaction has committed, because we have a commit record, which just says what the TID is that's committed, and we actually have all the information at the backups, namely the the commit records, which describe the write transformations on the backups. And so during recovery, we actually have enough information to decide, that the transaction actually has committed. And so that's sufficient. Of course, there's a complex protocol that actually needs to go into action and sort of look at all the pieces that are left behind by the transaction, but there are enough pieces left behind for the transaction for the coordinate, for the sort of new coordinator or the recovery process to decide that actually this transaction indeed has committed and should be persisted. Okay. Good. So let me sort of summarize FaRM, and before we jump into the discussion of Spark. So, top level, what is sort of cool about FaRM is it's fast. It can execute many transactions per second. There are some restrictions, of course, on FaRM. You can't do it in all the time. So first of all, it assumes few conflicts. So it uses this optimistic concurrency control scheme. And the reason it uses this optimistic concurrency control scheme because it doesn't want to take out locks, because it wants to do these one-sided RMBMAs without actually any server involvement. So it uses an optimistic concurrency control scheme. That means that if you want to get good performance and avoid transaction boards, that the workload better actually have few conflicts. And we've seen in the evaluation that there are sort of the two common benchmarks that are being used in the transaction literature to measure systems. For those two benchmarks, clearly is doing extremely well. This does mean there are not that many conflicts. The second assumption it makes is that the data must fit in memory. So it either means that if you have a really big database, you have to buy more machines, or if you really the data is too big and you don't want to buy more machines, then basically you can't use FaRM, and you have to sort of go back to a sort of more traditional database that actually has persistent storage, and so that you can read and write records to a much larger storage device. Replication is only within the data center. So in that way, respect, it's quite different from Spanner, right? Where the whole goal there was to do synchronous transactions across, synchronous replication across data centers, to support applications that need to be able to survive or continue while some data centers are down. In the case of FaRM, that is just not the case. It's not targeted to those kinds of applications. And then the final point is, it requires pretty fancy or exotic hardware. In particular, it has sort of two things: this UPS, distributed UPS, to survive complete data center outages, and more importantly, it uses this RDMA NICs, to get actually really high performance. Okay, that's sort of all I wanted to say about FaRM, unless there are any further questions. Okay, so that basically ends our set of papers, or this ends the sort of transaction side of the of 824. So we've sort of done 3 lectures on transactions, and that's basically this is the end of talking about the transactions. So that will show up in other papers, but we're not going to talk about it in any more detail. And in fact, we're basically sort of done with talking about sort of the most challenging part in distributed systems, namely building fault-tolerant storage systems. And we're now seeing a broad spectrum of different designs, including designs that actually support this very powerful programming abstraction of transactions. So in this lecture, or the remaining of this lecture, and subsequent lectures, we're going to sort of look at different topics that are sort of unrelated to storage systems. And so the first topic that we're going to be talking about is Spark.